Hello, I'm Joe Valenzuela, and this was my topic of interest. Let me start with the question, how can you improve the compressibility of arbitrary text, in this case, English? Let's be a little bit more specific. Let's say we wanted to employ a common compression technique like runtime length encoding. Runtime length encoding, or RLE, represents repeated runs of the same symbol in a string with a count and the symbol instead. In this example, we've changed a character array encoding of the input string bookkeeper with an encoding that gives the symbol and the count. Whether this representation is small or not depends both on the implementation details of the encoding method and also the statistical properties of the input string. In general, the more characters repeat and the longer the runs, the better the compression. Words in English don't generally contain repeated characters. In the Jane Austen novel Pride and Prejudice, for example, characters only repeat about 3% of the time. A fact you may find interesting, however, is that if you sort Pride and Prejudice, the characters repeat almost 100% of the time. Can we exploit this fact to improve the compressibility of the original? The answer is yes, but before I explain how, let me talk about a naive approach. One thing that won't work generally is sorting the text and storing the indices alongside it. Why? Because the indices have the same statistical property as the input string, and thus will offer the same challenges to compressibility. Counterintuitively, though, there is something we can do to the original data to make it more compressible with no additional space requirements. This brings us to the Burrows-Wheeler transform, or BWT. BWT, which was introduced in 1994, allowed, to the shock and amazement of the world, a transformation on string text that radically improved compressibility, for English, while requiring no additional storage. And it does it in linear time, both in the encoder and decoder. First, let's talk about the encoding. We start with our input string, here the word banana, which has been marked with a start and end character. We generate all the rotations, aka cyclic shifts, of the string. Rotation is just a traversal of the characters of the string in order, starting at an offset, possibly 0, and wrapping around the end if necessary. We then do a lexical sort of these rotations. And then the encoding is the last column in our table. Take a moment to convince yourself that every character in the input string will appear there. Okay. Why does this result in a better statistical property in the output string for compression techniques like RLE? Because for languages like English, groups of letters don't occur with the same frequency. So A in the word banana is likely to be followed by the letter N. Consequently, when the rows that start with N group together lexically, the preceding character A occupies the previous character, modulo the circular shift boundary, which puts it in the final column. And there we go. Thanks for enjoying my presentation. Okay, I actually had people think that that's where the presentation ended, so let me just be a little bit quicker here. I'm going to talk a little bit now about the decoding process, which is where the real magic happens. The amazing thing about decoding is that it only takes 2 steps. 2 steps repeated n times, that is. The inverse BWT in a nutshell. First, we take the previous step's output string. Then we sort it. Then we prepend the output string, and then we sort it. Then we prepend the output string, and we sort it, and so on, so on, and so on, until we have our square decoding matrix. We can identify our input string in the decoding matrix because it ends with our terminal character. But why does it work, you may be asking yourself. Let's take a look at that final decoding matrix. Or maybe it's our encoding matrix? It doesn't matter, because they are identical. The output string exists in its final form in both. The output string contains all the characters from the input string. This is actually true for each row and each column in the encoding matrix, because each row starts at a different offset within a shift cycle. Sorting the column gives you the first column of the encoding matrix, which, after all, is just the characters in the input string in sorted order. When we prepend the output string to the left of our sorted column, that's step add number 2 in our decoding process, we'll generate 8 letter pairs. Each row of the final encoding matrix has one of these pairs in it, although not necessarily the same row as this mini table. How do we know this? We know the first column in our mini table matches the last column in the encoding table because that's where we got it. We know the second column in our mini table matches the first column in the encoding table because that is just the sorted characters in the input string. Since both of these columns exist in the encoding table, the rows have to match. For any row, we can find a rotation that starts with the character in the last column and proceeds to the character in the first column. For example, row 4 in the mini table starts with the start symbol and is followed by the letter B. This corresponds to the same row in the encoding table. Subsequently, we can find a rotation in row 7 that starts with the same two-character sequence. Since that's the case, it is also the case that after sorting our mini table, we've recreated the first two columns of the final encoding matrix. By induction, we will eventually reconstruct the entire table. The paper goes into a more rigorous proof. One property that this relies on, that I haven't mentioned yet, is our sorting needs to be stable. That is, the first instance of A is the same in both strings. The paper describes how you can exploit this fact to build a recursive lookup table, where the index in the first column of the current character gives the next character in the sequence of the output array. As an illustration, we'll start with the terminal character. Once we hit the start character, we know that we have traversed every character in order in the output string. And that's all I have to say about this amazing algorithm. Thank you very much.